Okay, back again. We're going to talk about a few specific cases that arise in the animal kingdom, including us animals, us mammals, us humans, and really describe some of the challenges that different animals face in their environment. Because this is, again, natural that we have either a challenge to, let's say, maintain our water concentrations. Sometimes we have the opposite situation of animals that live in fresh water, have to keep the fresh water from diluting the concentration of ions in or other particles in their own body and maintaining their osmolarity. One of the, I think, most interesting examples of an important difference arises when we have marine reptiles, for example. So you may know or may not have ever thought about this, but certainly at some level you kind of realize that drinking salt water is not a great idea. We see large-scale efforts to desalinize, to remove the salt from water, to make drinking water out of it. This is not just because it tastes badly. This also has to do with how it can affect our inner water concentration. Because it turns out that water, salt water, has a concentration of roughly 3% salt. And it turns out that our urine concentration, we as humans know, our urine concentration, our maximum concentration of urine that we can produce is only 2%. So that means that the water we're consuming has a higher concentration of salt than we can remove from the body. So if we keep drinking this water, we'll actually accumulate salt. And if we accumulate salt, that'll shift our osmolarity in the wrong direction. It'll increase it too high, and so the body will tend to produce more water to get rid of that extra salt. And the only way we have to get rid of it is to dilute it and put it in our urines. And so at the end of the day, when we drink a liter of salt water, let's say, we have to remove more than a liter of water from our bodies to deal with that load, that salt load that we incur. So drinking salt water just doesn't work physiologically, independent of lots of other things about drinking salt water. Marine birds, on the other hand, of course, need to be able to consume water as they fly over the ocean, and they do fly incredible distances in their migration patterns. And so they, one could argue, might have a superior kidney that would produce a higher concentration of salt. And indeed, they do have a superior kidney, but not that superior. So it is able to produce urine with a concentration of about the same as seawater. So they can produce a 3% salt solution in their urine, whereas we're only 2%. But that really doesn't help them in the sense that just maintains the balance. It doesn't allow them to benefit from that, any additional water. What they have in addition to that is a whole separate system that creates a concentrated salt solution from the plasma salt. And so they're able to produce a concentrated solution of 5% salt and then excrete that through little holes in the sides of their beaks, actually. So they can get rid of that extra salt and ultimately benefit from the salt water that they consume. So they can increase the amount of salt in their system. And this brings us to the point that the challenge for an animal like a seabird is to maintain hydration even in the absence of fresh water, largely. I mean, these seabirds, they spend most of their lives on oceans. And so this is how those particular systems have adapted to that situation. Now, freshwater animals have a different challenge. As I said, they're living in an environment in which they're surrounded by fresh water, which has a very low salt concentration. So the risk in that case is that water diluting the concentration of particles in their bodies and hence sort of wash them down. So they also have a blood concentration, for example, that is hyperosmotic, so it has a higher density compared to the surrounding tissues. This becomes one of the metrics we can use in these various comparisons. So the blood concentration is hyperosmotic compared to the surrounding liquid in which they live. And so they have to produce a hypoosmotic urine. So they need to get rid of extra water. Their water is passing through their body. They don't drink it per se, but they do pick it up inevitably as the water that flows by their gills, which they of course need for respiration. some of that water actually enters the body, but they don't actually drink water on top of that. So they get easily enough water. In fact, they have to have the ability to produce a low density, low concentration, hypotonic or hypoosmotic urine in order to maintain their particular balance. Amphibians are in a similar situation where they have a hyperosmotic blood plasma concentration, and the urine concentration that they produce is also hypoosmotic. So they have the similar challenge, and they actually are able to maintain their osmotic balance to another mechanism, and that is through their skin. So the skin is not only capable of moving water, but it's also capable of absorbing salts. So if there are low concentration salts even in their external environment, and there are inevitably salts even in what we call fresh water, it's not distilled water, they're able to absorb that and hence increase the osmolarity inside their bodies and maintain their actual balance. And so we see this is pretty typical of the different situations that each animal faces in their environment. Again, as I mentioned, marine birds have one set of solutions. Marine mammals have a different set of solutions. So if we have there are, again, two different types of marine fish that we have to think about. The teleosts are the ones that we've kind of described before. These are fish that have this hypoosmotic blood concentration. They're able to actually drink seawater, but also secrete salt, but this time from their gills. So unlike the seabirds that have the concentrating organ and orifices that allow that solution to leave, the teleost fish have gills, and those gills they actually perform a lot of the functions that we see in other organs like kidneys in other mammals. And so those gills allow them to remove salt. And so even though they're living in a salt environment, and even though they're drinking seawater, they can get rid of that extra salt. Now the subset of animals, sea animals that include sharks, for example, they do not drink seawater. They don't have that same mechanism, but they have yet another one that creates, more like the seabirds in a sense, can concentrate a solution of salt and excrete it from a separate gland that exists in their bodies. Now, another challenge you might have thought about is, what do those animals do like salmon, who spend part of their lives in freshwater and part of their lives in seawater? Right? So fresh salmon are born in fresh water, swim to the ocean, spend time in the ocean, and then swim back. At least some species do. And there are other fish who have that capability. So what happens when they change environments? Because then their whole balance, the whole set of challenges changes. And indeed, they're able to adapt very quickly, to conform to some extent to the external setting they're dealing with. What you see in this plot is on the x-axis, what happens in one of these fish when they move from freshwater to seawater. And what we see here is the plasma concentration of cortisol and sodium. So cortisol is usually a stress substance, stress hormone, and of course, suddenly being dumped in salt water is probably stressful for them. It would have all kinds of downstream regulatory impacts in these fish. We see an increase in intracellular or plasma sodium concentration initially, so you see it takes several days, but that after about a week, the sodium concentration in the plasma has gone back down to normal, which is kind of amazing. So how do they do that? Again, it's the gills. So the gills are able to move the sodium out of the body. And that's what you see in the lower plot here is, again, over this same span of time, we see this rate at which salt leaves the fish through the gills increases somewhat dramatically. I don't know all the details of how this reorganization or redesigning almost, or certainly implementation of this salt extraction mechanism works, how it's upregulated, but it is over this sort of time course, and allows the salmon to maintain their intracellular osmolarity, even though their external space has changed so dramatically. Okay, so now we move to the air-breathing animals. So these are animals that may or may not live in water or air, but are air-breathing. So what we have here are the marine reptiles, for example. We have marine mammals, whales, you can think about that. Marine birds, we've talked about already. And of course, birds, the terrestrial birds, the birds that can have fresh water around them. And you see each one of them adapts a different way. We see desert mammals, we'll come back to one of those, for example, drinks no water and is able to create enough water through metabolism, through the byproducts of consuming the food that they eat. Their urine concentration is hyperosmotic, and that's certainly true of most of these. So they have a hyperosmotic concentration. Turtles are different again. They have an isoosmotic concentration. So each animal is adapting somewhat differently. Their big challenge, of course, is dehydration, because they're not surrounded by water. In general, are surrounded by air, and there are different solutions for how they do that. Now, what about land mammals? So there the challenge is dehydration again. They can't drink seawater, as we've said. So their whole goal is to maintain water and reduce the inevitable losses that incur. And there are a number of solutions that different land mammals have found for that. Even we as humans know that when it gets hot and there's a risk of water loss, we tend to try and seek out cool places, and we tend to reduce our activity level. Both of those reduces the amount of water loss. You remember that increased heat, for example, increases our respiratory water loss, and certainly increased activity, physical activity, increases our water loss through perspiration. So we tend to seek out local conditions that reduce that inevitable water loss. We produce concentrated urine. In some animals, they're able to produce very dry feces. You see this in our local climate with deer, for example, and moose. They produce a fairly dry feces compared to other animals. These animals are also capable of making use of metabolic water, which, as you saw in that first table in the previous video, is a substantial amount of water. And some animals, and we'll come back to the famous one, the camel, can tolerate really wide fluctuations in hydration, something that we as humans are not nearly as good at. So here's a little table that shows the production of metabolic water during the oxidation of foods for different food groups. So this is the grams of metabolic water per gram of food. We can see carbohydrates are pretty good, fats are the best, and proteins are a little bit less. And then there's even a kilojoules expended, so there's sort of an energy balance that we can also normalize by. So this is grams of metabolic water per kilojoule expended. And again, this allows us to sort of balance water and energy needs and losses along the way. Now here's some numbers in humans, just to, again, put this in context. We've seen these before. This is our different losses at normal temperatures, hot temperature, and during exercise from the different elements or pathways that we have. Literally, what goes through our skin, our lungs, our feces, urine, and of course through sweat, which is the single largest one, especially when we're exercising. Now let's talk about, as you all know, my favorite little critter called the kangaroo rat. They live in southern Utah. They live in southern California, dry climates generally. These animals never drink. They never drink any water. There's no water around. They live in a truly dry climate. They might, of course, get a little seasonal water at times, but in general, they don't. So how do they actually survive? So they do those things that we mentioned before. They are only active at night, so they live in burrows during the day. That reduces the temperature that they're exposed to compared to the surface. Those burrows also maintain a certain humidity, so it turns out in a more humid setting, there's less water loss in respiration. That helps them. They have long snouts, long noses, and those help them also to reduce the amount of water loss in respiration. They are also capable of producing highly concentrated urine and very dry feces. So they have taken all these systems that all mammals share and evolved to the point where they really are masters at this whole game of water preservation. Now, inevitably, they do overheat at times. They're certainly exposed to some situations that bring their body temperatures up and have to get rid of that heat. So instead of sweating, which they don't do, they produce this saliva that wets the area around their chin, the fur in their chin, and that provides evaporative cooling. They live in dry places, so evaporative cooling can work quite well. you see that their metabolic water makes up about 90% of the water that they consume. There's a little bit of water also in the food itself. So naturally, fruit contains a lot of water, grains contain much less. So there's something like 10% of their water they get that way, but in general, none of it is through drinking. And they're able to reduce their losses, their inevitable losses, again, by concentrating urine, concentrating feces, and living in a cool setting as much as they can to reduce the loss. Now, of course, we have to talk about the camel, which is kind of an amazing creature. And they're capable, as we know, of a number of measures to deal with heat, not just water loss, but to deal with the heat of their environment quite effectively. So, for example, they're very slow breathing. They reduce the amount, and by literally reducing the velocity of the breath, that allows more time for some of that moisture leaving in the fully saturated air to be recovered. And they also, and this has nothing to do with water loss, but in order to deal with the heat, instead of having fat uniformly distributed over their bodies and providing an insulating layer that they really don't need or don't benefit from, they concentrate that fat in the hump. So a large part of that hump that inevitably we think about with camels, whether it's one or two humps, that's actually mostly there for fat storage. And then the rest of their body can be very lean and not suffer from this insulating effect of the fat. They have a thick, wiry coat that actually provides shade. So it's not a woolly coat, as you would think, and it's not just a hairy coat, but it's fairly thick and actually literally provides some reflection of sun and then some shade on the actual skin. They're also tall animals in the sense they have long legs for their body size compared to other animals, and that lifting of their body away from the ground reduces the heat that they would feel from the ground. In these very hot climates, of course, there's a great deal of heat radiating from the ground. Naturally, as you would expect, they can produce very concentrated urine, and what makes them really unusual is that they tolerate remarkable variations in their hydration levels. They also handle very poor water quality. They have good, ways of filtering that water and metabolizing away those toxic agents that we would find intolerable. They also can tolerate an enormous variation in body temperature, something that we as humans certainly can't. Their body temperatures can range from 34 to 41 degrees Celsius, 37 of course is normal, and we tolerate 1 or 2 degrees around that before we get into serious trouble, and they have a much wider range of temperatures that they can handle. The other thing they can do is consume enormous amounts of water at a time. Of course, they're famous for that. They get to a watering hole, they drink some ridiculous amount, up to 25% of their body weight. It turns out we as humans literally die at about 12%. So if we try and drink a lot of water, we regurgitate it, we throw it up again. We cannot consume large amounts of water at a time. It dilutes all the solutes too dramatically, too quickly, and our bodies can't handle it, whereas camels have the ability to do that. They can drink up to 200 liters at a time, 130 just in a few minutes. And so camels have that ability to buffer that increase in water concentration and not have their plasma concentration of water change as dramatically as it would in other mammals. So they're truly remarkable animals. And as we see, they tolerate, here's a graph showing, for example, the rectal temperature in a camel, and that tolerance changes in their watered or sort of more dehydrated conditions. So you're going to see the red curve is the dehydrated curve with dramatic variations in internal temperatures, which get moderated when they actually have water on board, when they can afford to use some of that water, evaporative water, for cooling. So they really are kind of amazing. And finally, insects. Their challenge, like all of us terrestrial animals, is dehydrations. and they're actually capable of extracting water from the air. So they have, and again, another unique ability. They can also do the usual things: concentrate their urine, produce high concentrated salt solutions that they can get rid of. They have water capillaries between the hairs that absorb water from the air. That's the mechanism they use to do that. As we saw before, they have this sort of waxy skin coating to reduce the amount of water they would lose through their skins or their outer shells, and manage to preserve things. The last critter I have to tell you about and talk to you about a little bit, of course, because it's a Utah phenomenon, is the brine shrimp. Now, the brine shrimp are completely exceptional in the sense that they, in their encapsulated form, can stay alive and not have any water loss whatsoever. So they can go into a dormant state and can survive for years without any additional water, and literally survive. And they're not plants. These really are animals, which is why they were sold for years in the back of comic books. Most of you have never seen a comic book, maybe, but for many of us growing up, there were these things called comic books, and in those comic books, there were always ads for these things called sea monkeys, and you can look this up. They're what you would send your $1.25, as you see in this figure, to get an envelope where they would literally send you a little envelope of these little things that look like seeds, and you put them in the water and they'd magically come to life. And those, they're very small, of course. They're not the most exciting pets to have around in that sense, but the brine shrimp really are amazing in their ability to tolerate all kinds of really difficult environmental conditions, including the high salt concentration in our own Great Salt Lake. And hence, brine shrimp are an important local industry here in Utah, and they're used for fish food, and a few of them get sent out to inquisitive young people to look at them in their aquariums. So hopefully it gives you a sense of how different animals adapt to these very different stresses in this sort of general context that we set out from the beginning of this course, and that is to spend a little bit of time examining how different animals have physiological solutions, can deal with physiological challenges in different ways, different from us, so that we can then both appreciate that from a sort of almost aesthetic perspective, but also use it to think about how we might replace our organ systems with functionality that we derive from the way animals solve these same problems. So hopefully it broadens our scope of understanding and our arsenal of approaches we can take in the context of, let's say, artificial organs to, again, augment or replace functional losses in humans in a medical context. So hopefully that was a little fun and interesting and captured your appreciation or increased your appreciation for these funny little creatures that we see running around us and how they cope with situations and are able to do things in some regards in a much more exorbitant and enhanced way than even us majestical humans. So thanks for your attention, and we'll see you soon. Bye for now.